Welcome back. In this video, we look at techniques that are often discussed in an AI context as well as machine learning. First, we look at Markov models and hidden Markov models. Then we'll discuss reinforcement learning. A Markov model is used to model probabilistic events. The model consists of a set of states and transition probabilities between states. Here we see two states, E representing the state of exercising today, and N representing the state of not exercising today. In state E, there's a 20% probability of moving to the N state, which means there's an 80% probability of staying in the E state. Likewise, state N has a 25% chance of moving to the E state, so the chance of staying at state N is 75%. The Markov assumption in a Markov model is the assumption that the current state depends only on one prior state. Let's look at how we could model this in simple code. I've put the four transition probabilities into a transition matrix, and I've initialized the model with the situation where a person exercised only 5 days out of the month and didn't exercise 25 days. And that's what we see here. Then I'm just going to iterate 10 times through multiplying the transition matrix times the current state, which will update the current state. And let's see what happens. And you can see after about 5 or 6 iterations, the model stabilizes. That happens sometimes in Markov models. And even if we run this for 5,000 times, it will still be at about 55% exercise and 45% not exercise. It will change very slightly at each iteration, but it has stabilized at these values. And it may seem counterintuitive, but it doesn't matter what our initial states are. It will still converge at the same probabilities. In a Markov model, we know the transition probabilities between states. But what if we want to model a situation where we don't know those probabilities? We can do that with a hidden Markov model. The hidden Markov model has various states that we can observe. These are the x's. And it assumes that there are hidden states, we'll call those z's, that we cannot observe directly. It is these hidden states that have the transition probabilities. These hidden states manifest the visible states that we see. The transition probabilities can be discovered simply by observing the X state data. Let's look at an R package that can do this. I'm going to use R package deepmix S4. The S4 refers to the underlying type of R object that it uses. This is a more modern type. And I'm first just setting up using some basic R, a repetition of what actually happened, the observations. Did I exercise or did I not? For 7 days a week, for 10 weeks. These are my X states, the observed data. And then we'll just let deepmix do its thing. And we can see the plots over here. And what the plot is actually showing is what happened, the actual observations X here, which is that this person exercised only on the weekends. And here we see the estimates that it learned from the model. We can print those out as well. So how did this magic happen? It's an iterative learning process. First, it observes the next state. Then it estimates the probabilities that would have gotten you to that state. And then it repeats. If this seems vaguely familiar, it's because it's a variation of the EM expectation maximum algorithm we saw in k-means. Let's look at an example on the S&P 500 data that's built into this package. So all I have to do is load it. And then let's take a look at it. It's S&P 500 data all the way back to 1950. It has the open, the high, the low, the closing, and the volume. This last column is the log of the ratio between the previous 2 days. So we'd look at the closing for this day divided by the closing of the previous day and take the log of that. And this is its range, not a terribly large range. Here we're going to build our model and plot. The bottom data is the actual log-reg data that we saw, and this top graph is predicting trends upward, and the bottom graph is predicting trends downward. A lot of financial models are built on HMMs, and it's not hard to see the utility of this type of model, but it has a fundamental problem in that it cannot foresee what it cannot foresee, so-called black swan events. Black swan events are extremely rare events that have an extreme impact on the market, and everyone after the fact says that it was obvious in hindsight, but no one really took it seriously beforehand. So I would always take this kind of financial model with a grain of salt. Reinforcement learning also models an environment, and it often assumes there is some underlying hidden Markov model which it will have to learn as it goes along. The hidden Markov model we looked at learned from looking at past data, and some reinforcement learning models will jumpstart learning that way, but the main form of learning in reinforcement learning is learning from interaction with an environment. There's an agent who makes decisions in the environment with a goal of maximizing some reward. So learning is based on taking an action and observing the outcome. This is sometimes described as the way we humans learn. We try something, see if it works. If not, we try something else. I'm sharing notes here from my AI professor at UNT, Kathy Swigger, who was also on my PhD committee. So we have an iterative process here where an agent will take an action, and there'll be a predefined set of possible actions. This action has an effect on the environment and changes the state, and the agent will receive a reward. It does assume some decision process. We will have a set of states, a set of actions, and a model of going from one state to another, and a corresponding set of rewards. When we start off, we don't know the transition probabilities and we don't know the rewards. These have to be learned in the process of just taking actions. What we're looking for is a policy that will give the best action for each possible state to maximize the expected reward. This is sometimes called Q-learning, and there is a bit of randomness in here. So the learner can choose to follow one of the previously defined paths, or it may choose a random path, and in this way it can find new paths through the environment. There's a gamma discount factor for how much we're going to reward short-term rewards versus long-term rewards. Let's look at a simple example. Here's a grid world. An agent is going to start here and can move certain places, can't move other places, may hit a wall. And it could get a negative reward. The ultimate goal is to get to one of these +1 reward locations. So you can see there are many ways that that could happen. So given a location, there are 4 possible moves: up, down, right, left, although it's not always possible to move in every direction. Any squares that are blank here will have a very low default value. Here's an algorithm, how it could work. We have to initialize an environment, the starting point, some different parameters, as well as a move limit. The gamma we talked about, the alpha is a parameter controlling how much we want to randomly choose a move or go with what we've done before. We can initialize the Q values based on the grid environment, and then we'll start iterating and learning. And as long as we haven't achieved the goal, we'll pick a move, make the move, and update the Q values. Before doing that, we'll have to initialize a row by column by 4 matrix, 4 because of the 4 possible moves, up, down, left, right. We'll initialize those to a small negative value. And then as we go, we're updating the Q values with information from the environment. Here's a sample solution to solving that grid world problem. This code is in the GitHub. Caveat here, I wrote this code a long time ago, and when I looked at it recently, I see some flaws in it, but it could give you the basic idea of what's going on. So in the main routine down here, we're going to try different learning episodes, and as long as it's not a goal, we're going to loop through the algorithm, making moves and accumulating the rewards. And we see in the run down here that these are our starting cute values. You can see that most are 0.01 negative. Some are -1, and there's a couple that are +1. We ran through a few learning episodes, and it learned in as many as 29 moves, as few as 16 moves. So it kind of converged here and found an optimal path. This is a very simplified example of reinforcement learning, just for illustration purposes. R does have some packages for reinforcement learning, one of which is called reinforcement learning, and it has a simple Gridworld problem as well. You can see an example of that in GitHub. Reinforcement learning has deep roots in AI using Markov foundations. The most exciting trend in reinforcement learning is deep reinforcement learning, which is allowing systems to scale to problems unimaginable with traditional approaches. I have some links at the end of the chapter to learn more.